Today we're going to cover two last little topics. Voltage regulation and transformer efficiency. So the voltage regulation of a transformer is the change, thank you, in the magnitude of the secondary terminal voltage from no load to full load. When the primary voltage is constant. Or mathematically, we're going to define it as a percent voltage regulation. And this is going to be the magnitude of V2 under no load conditions minus the magnitude of V2, our secondary voltage under full load conditions, divided by the magnitude of V2 under full load conditions times 100%, where full load just means the rated load of the secondary. Okay, so let me write that down just to be clear. The term V2 no load is the same as the magnitude of the voltage at the primary V1 divided by our turns ratio A with all parameters referred to the secondary of the transformer.
The full load is the, what is that word?
Rated. So secondary of the transformer, and using this relationship, we can then say that the quantity V1 over A, now this is not the magnitude of it, we'll use that in a minute, is our secondary voltage plus our secondary current times REQS plus J XEQS, or our series equivalent impedance when referred to the secondary side. So let's put this expression into use. Let's say that we have a 100 kilovolt ampere, 7200 to 240 volt transformer. It has the open circuit and short circuit tests applied to it. And the following data is collected. So for the open circuit test, Yes. Our voltmeter measures an open circuit voltage of 7,200. Our ammeter measures an open circuit current of 0.65 amps RMS. And our wattmeter measures an open circuit power of 425 watts. Our short circuit test is also applied at our high voltage windings. And we find that we have a short circuit voltage magnitude of 250 volts RMS, a short circuit current magnitude of 13.889 amps RMS, and a measured short circuit power of 1,420 watts. The transformer is connected to a full load, which means it's delivering rated voltage and current at the secondary. Which operates at a power factor of 0.90 lagging. And we want to determine the voltage regulation of the transformer. Yes, ma'am. So those are measured quantities from a test that is carried out.
So like, is that?
Yeah, all of this information is given in the problem statement, but like if you wanted to carry out your short circuit test, you would literally short circuit. So in this particular case, the short out on the high voltage windings.
So like, nothing really so far, but,
Correct. Yes. Okay. And now we're going to figure out what the voltage regulation is. So this is our goal here. This bit, okay. So effectively what we're going to be doing is we're going to apply this equation, which in turn causes us to have to apply this equation, okay? Because that quantity V2 no load is the magnitude of V1 over A, okay? So let's start by figuring out the V1 over A bit, because that's probably the hardest part of this thing to do, okay? So we need to know our secondary voltage, all right? So this part right here, how do we figure that out? Anybody have a thought? So our transformer is operating at full load, which means the secondary has rated voltage and rated current, okay? So if our transformer is rated for 240 volts RMS on the secondary, then I would argue that V2 is 240 volts RMS, okay? Now, I'm actually going to modify this very, very slightly, okay? I'm going to call it 240 angle 0 degrees volts RMS. So effectively what I'm doing here is I'm assuming a phase angle for the voltage. And I'm just saying it's 0 to make the math easy. And then our current I2 is going to be found with respect to that particular voltage. Jacob, what's up? Mhm. Yeah, so no, so I can understand why you might be confused by that, because the short circuit voltage, VSC, is 250 volts RMS, but this is when our test is applied on the high voltage side, right? So on the high voltage side, we're going to be using a reduced voltage, so something less than 7,200 volts. Well, 250 volts RMS is significantly less than 7,200 volts RMS. If we had performed the short circuit test on the low voltage side, we would expect a number much smaller than the rated voltage on the low voltage side, okay? So both of these were performed on the high voltage side, so everything is checking out. Our open circuit voltage on the high voltage side is exactly rated voltage. Our short circuit voltage, when the test is performed on the high voltage side, should be less than rated voltage on the high voltage side. All right, so we figured out V2. So now let's talk about I2. Okay, let's just take these bits of this equation one by one and figure them out. So once again, our transformer is operating under full load, so we are expecting to have rated current. So what's the magnitude of our rated current I2 going to be? So that's going to simply be our rated apparent power, S, divided by the magnitude of our rated voltage, or 100 kilovolt amperes, divided by that 240 volts RMS, which I get to be 416.667 amps RMS. Now we don't get to assume a phase angle for our current here, because we're told specifically that our load is operating at a particular power factor, and that power factor is going to be related to the phase angle of our current under the assumption that the phase angle of the voltage is 0, right? So a power factor of 90% lagging means that our phase angle, so I'm just going to call this theta IS, is going to be negative the inverse cosine of our power factor. So that's negative the inverse cosine of 0.90, and that is going to be equal to negative 25.842 degrees. So some of you, justifiably so, might be confused as to where the heck that negative sign is coming from. I don't know how you all were taught how to deal with power factor and all that kind of stuff. But for a lagging power factor, how I was taught was that a lagging power factor should give you a positive phase angle, okay? So a lagging power factor will give you a positive phase angle for the complex power, but the the phase angle for our current here has to be of the opposite sign, because if you recall, complex power S is equal to V times I conjugate. So the negative sign right here is effectively taking into account that we're taking the conjugate of the current to come up with our complex power. Okay. So that in turn means, just for those of you that are paying attention, if our power factor were leading, the angle of our current would be positive, and the angle of our apparent power would, or our complex power would be negative. So putting these things together, our RMS phasor current I2 is 416.667 angle negative 25.842 degrees. Amps RMS. So I'm just going to scroll up here real quick. We figured out what V2 is. We figured out what I2 is. So now we need to figure out what effectively the equivalent impedance of the transformer is, referred to the secondary or low voltage side. Okay. So one thing that I want to point out here, we don't need to know what the core resistance is or the magnetizing resistance. We only need the series components for this, okay? So the equivalent resistance on the high voltage side, we talked about this in class the last time we met. So our equation there is our short circuit power divided by the magnitude of our short circuit current squared. So that's going to be 1,420 watts divided by 13.889 amps RMS quantity squared, which comes out to be 7.361 ohms. Since we want this referred to our secondary side or our low voltage side, what do we need to do? Are we multiplying by a squared or dividing by a squared? Dividing by a squared because we're going from the primary to the secondary. Absolutely correct. So REQ low voltage or REQS is going to be 7.361 ohms times 240 over 7,200 squared, or I'm saying dividing by a squared is effectively multiplying by the reciprocal squared. And that's going to get us a resistance of 8.179. My stylus will write. Milliohms. Now we need to figure out what the reactance portion of our impedance is. So recall that the equation for XEQ is the ratio of our short circuit voltage magnitude over our short circuit current magnitude quantity squared minus our resistance squared. So substituting in my numbers here, this is going to look like 250 volts RMS over 13.889 amps RMS quantity squared minus that 7.361 ohms quantity squared, which comes out to be 16.426 ohms. And then referring that to the low voltage side is going to be XEQ high voltage times 1 over a squared, or 16.426 ohms times that same factor, 240 over 7,200 quantity squared, which gives me 18.251 milliohms. So we now have all of the different parts of this portion, right? We just figured out what REQS is because that's the REQ on the low voltage side. We figured out what XEQS is because that's the XEQ on the low voltage side. So we have that whole quantity V1 over A. So, yes, ma'am.
Okay, so wait,
Yes.
okay, so. Oh, you just like,
I did the exact same thing that I did for the resistance. So our turns ratio is defined, A is defined to be the primary side voltage over the secondary side voltage, which would be 7,200 over 240. So when I'm dividing by A, that's the same thing as multiplying by 240 over 7,200. Well, since I'm dividing by A squared, I'm squaring that factor. All right, so we're going to put all of the work that we've done together, and we're going to find the quantity V1 over A as a total thing. So that is, again, V2 plus I2 times REQ low voltage plus J XEQ low voltage. So just substituting in numbers here, that's going to look like 240 angle 0 degrees volts RMS plus 416.667 angle negative, did I write it down? 25.842 degrees amps RMS times 8.179 plus J18. My stylus isn't working here. 18.251 milliohms. And in polar coordinates, this comes out to be 246.440 with a phase angle of positive 1.245 degrees volts RMS. I cannot emphasize enough how much having a calculator that can do the complex math for you will make your life easier. So if you have not already done so, I cannot recommend enough you going and spending the $20 to get one that does it. All right, so this is the hard part, okay? Now we're at the easy part. Our percent voltage regulation is just going to be the magnitude of V1 over A minus the magnitude of V2 rated, which we already know, over V2 times 100%. So what's the magnitude of V1 over A? Tell me. What was that? 246.44. Throw away the angle stuff, right? What's the magnitude of V2 at rated load? 240. All right, and so that comes out to be 2.683% voltage regulation. If our load were operating at a leading power factor, we would expect to see a negative voltage regulation percent. Okay. All right, so what I just did there is extraordinarily similar to what I asked you to do on your homework assignment and what I'm going to ask you to do on the exam. It's literally going to be just that with different numbers. Okay. So now let's talk about efficiency. This is a little bit easier. How do we measure the efficiency of anything? Percentages. It'll come out to be a percentage, sure. Output over input. That's it. Okay. So our transformer efficiency, eta, or Greek fancy looking N, is just going to be our output power over our input power. Okay. Well, we can re-express our input power as, so let me put P out here. The sum of our output power plus any losses that are occurred or incurred. Okay. Well, what kind of losses do we have in a transformer? We've talked about both, right? So the losses are what the resistive part of our transformer equivalent circuit is taking into account, right? So we're going to have some core losses and we're going to have some copper losses due to our windings, right? So we can rewrite this as P out over P out plus P core plus P copper. Well, our core losses are what we get as a result of our open circuit test. So that part is just POC. Our copper losses are what we get as the result from our short circuit test. That's literally what our watt meter is measuring. So the only thing that we need to figure out how to determine is our output power. Well, our output power is just going to be our rated apparent power multiplied by the power factor at which the load operates. That's it. So if we wanted to determine the efficiency of the transformer from the previous example. Yes. Load, because it's the power factor at which the load is operating. Yep. Determine the efficiency of the transformer from the previous example problem. So our efficiency is going to be our rated apparent power times the power factor of our load over our rated apparent power times the power factor of our load plus POC plus PSC. So what was our rated apparent power? 100 kVA. What was our power factor? 90%, 0.9. Same thing's going to go down here. What were our core losses? $425 watts. What were our copper losses? 1420, right? PSC 1420. And from this, we get, let's fancy it up here. I'm going to multiply it by 100% to get my efficiency as a percentage. And that's going to be 97.991%. All right, so that's the last thing that I expect you guys to know for your upcoming exam. So I posted a homework assignment over the weekend. Yesterday, I went through and I posted all of the answers to that particular homework assignment so that you can have them to guide you for your work. I also went through and posted all of my MathCAD solutions for all of the previous in-class assignments and all that kind of good stuff because I got too lazy trying to type things out. So I was just like, well, screw it. I'm going to give you what I have so that at least you have something. So here's what you should expect for your test. Let's look at the old homework assignments here real quick. Dropbox. 360. Have not made out the exam yet. That's what I intend to do this afternoon. So let's look at homework 1. So something in the vein of problems 1 and 2, some combination thereof, will be your first problem, okay? So effectively, I'm going to give you some core structure with a single coil on it. I'm going to expect you to be able to determine the equivalent reluctance and the flux through any given part of it, possibly the B field through any given part of it. I think I might take it easy on you guys and not make you pull anything from a table or pull anything from a graph like I had you do on one of the homework assignments. Just for time's sake, I don't think I'm going to be that mean to you guys on Thursday. So yeah, you're welcome. I'm very magnanimous. Being a jackass. So something along this line, right? So I give you some sort of core structure, nothing particularly wild, probably an air gap or something in there at some point. And you just need to figure out equivalent reluctance, you know, common things, flux, current, B field level. Nothing different than what I've asked you to do on the homeworks, okay? So that's your first problem. Your second problem is going to be more in line with the first problem from homework number 3, okay? So I'm going to give you a core. It's not going to be as complicated as this one. It's going to have 2 coils on it. I'm going to ask you to find the equivalent reluctance seen by the first coil and the self-inductance of the first coil. I'm going to ask you to find the equivalent reluctance seen by the second coil and the self-inductance of the second coil, and then the mutual inductance between the 2 coils. So that's something that we've done. And it's something that I've asked you to do. I'm happy to answer questions about that in a minute. I'm telling you what I'm putting on the test first, okay? So that our review section can be very targeted if it needs to be. Yes. So a core with 2 coils, equivalent reluctance seen by coil 1. Self-inductance of coil 1. Equivalent reluctance of coil 2. Self-inductance of coil 2. And then mutual inductance between the 2 coils. So to review what that looks like, we will very likely just work problem 1 here in a moment. Because problem 1 is effectively what I'm going to give you on your exam, except I'm going to make the geometry easier so that you have time to do it. Okay. Your last problem on your test is going to be effectively problem 5 from this homework set. So I'm going to ask you to give me an equivalent circuit referred to the low voltage side. And then I'm going to ask you to calculate the efficiency and the voltage regulation based on the data in the table. So exactly like the last couple of example problems that we worked, and pretty much exactly like problem 5 here. I have not decided if I'm going to give you all of the data from the high voltage side or one part from the high voltage side, one part from the low voltage side. Haven't figured that part out yet, but I expect you to be able to tell me, you know, if I give it to you on the low voltage side, then that's what you're looking for. If I give it to you on the high voltage side, refer it to the low voltage side, that kind of thing. Does any of that seem utterly ludicrous? Yes.
You said like we're gonna have test problem. Find this. We're going to find the sort of thing to that.
Yeah, so effectively, I'm going to expect you to do something almost exactly like problem 5 from this homework set for your test.
So
It'll have different numbers, but if you can do problem 5, you can do the test. If I tell you, give me the equivalent circuit, draw it out. Yeah. I'm lazy, so I'm just giving you the parameters because I don't want to have to get another program out to write these homework assignment answers, but yeah. Yes. Sure, we'll take it. Well, problem 1 is the one. Yeah, sure. So let's talk about, let's scroll up here and look at problem 1. That being said, problem 5, just so we're on board, is literally the examples we worked here a moment ago, except different numbers. So if you could follow along with the example that we just finished working, you can do problem 5. But all right.
It's like almost reduced to tears because like
We-
2%.
Yep. That's well, now that we've covered it, your life should be slightly less of a pain in the ass.
Why I was down about it. I guess that's what
All right, so let's look at homework 3, problem 1. And by the way, this is still very much due Thursday because I want you to do this to study for your test. So I got to draw this thing. Let me see. Let me get my mouse out if I can just drag it over.
Not that your drawings are not.
Oh, no. It would save us time and effort
I think
if I'm lazy enough to get my mouse out of my computer bag. Let me put my pen on as well so I can control V this guy. Yeah, all right, great. That saves us, I don't know, 5 minutes. All right, so I'm going to do this the exact same way I've done every other one of these. I'm going to break it down into little sections, right? So this is going to be RL. This guy is going to be R top left. This is going to be R bottom left. This is going to be RM. This is going to be RG2. This bit right here is going to be R top right in series with RG1. RR. And R bottom right, so BR. So nothing wild or crazy here, just breaking things down, right? So we do need a couple of pieces of information from the problem statement, so let me find those real quick. So our thickness is 8 centimeters, so let's write that down. I need to know the length of gap 1, the length of gap 2, and the core permeability. So let's see. So half a centimeter, 3/10 of a centimeter, and 12,000 mu naught. So half, 0.5, 0.3, and 12,000. Okay. So let's start with RTL. We have some length, right? Because reluctance is always going to be length over permittivity times area, okay? So what's our length going to be? So it's going to be half of 100 centimeters. And then from that, I'm going to subtract half of that 10 centimeter width on the left-hand side. And I'm also going to subtract half of that 15 centimeter width on the right-hand side. Then I'm going to have 12,000 times 4 pi times 10 to the minus 9 henries per centimeter. And then I have my area. Well, my area is just going to be the thickness, which is 8 centimeters, times the, I don't know, I guess call it height. Effectively, I'm trying to find this cross-sectional area where this bit right here is T, so the other dimension is going to be the 10 centimeters. I can't think of a word to describe it. And then I'll throw that into my calculator. Shit. And I will get some number. And apparently that diamond cross-sectional area is just going to stay there, so I don't erase things. All right, so let's throw this in our calculator and figure out what's what. So 100 minus 10 minus 15 over 12,000 times 4 pi times 10 to the minus 9 times 8 times 10. 3,108, exactly what you suggested, Jules. Thank you. 3.108 times 10 to the 3 amps per Weber. And while we're at it, we can say that our bottom left and our bottom right will be the same thing, because they all have the same dimensions, same cross-sectional area, and are made of the same material. So just for the sake of argument, I'm going to check this guy off, and this guy off. Now let's do the top right. So that's going to be the exact same length as we had for the top left, minus the length of that gap, right? So throwing that into my calculator real quick, or at least as quickly as I'm able to do so. Half times 100 minus 10 minus 15 minus 0.5 12,000 times 4 pi. But 10 to the minus 9 times 8 times 10. 3.067 times 10 to the 3. Amps per Weber. I'm gonna put a little check mark by this guy. Let's do RL. So that length is going to be the 40 centimeters minus 10 centimeters. Yes, ma'am. Oh, turns are dimensionless, so I'm just being lazy and not writing down turns. Doesn't particularly matter. Amp turns per Weber is the exact same thing dimensionally as amps per Weber, so. I am good either way. And if you look at my solutions to any of the in-class assignments, because it's on MathCAD and turns isn't a unit that exists in MathCAD, it's not going to show up there, but I do have them all expressed in amps per Weber instead of inverse Henrys or whatever the hell it comes out to be. So. And then we're gonna have, so this is a core part, so 12,000 4 pi times 10 to the minus 9 Henrys per centimeter times 8 centimeters times 10 centimeters. So 2,486.8, so 2.487 times 10 to the 3 amps per Weber. I'm gonna be lazy and trust joules. If you guys are okay with that. All right. So the quantity RR is going to be the exact same thing as RL because they are same dimensions and all that kind of jazz. So 2.487 times 10 to the 3 amps per Weber, or more correctly, Casey, thank you, amp turns per Weber. Check mark that, check mark that. We can go ahead and do RM here. So that's going to have the same length, except we're going to subtract LG2. Over that same 12,000 times 4 pi times 10 to the minus 9 Henrys per centimeter, 8 centimeter, 10 centimeter. You're absolutely right. Thank you for that. Yeah. Yeah, so the mistake I made there is that we're doing effectively this cross-sectional area here for the middle part. And so I had said mistakenly that it should have been the thickness 8 centimeters times the width of 10 centimeters, but obviously from the picture, the middle part has a width of 15. So if you don't put that in, you'll obviously get the wrong number. Let me throw this in the calculator. I didn't hear you. What you said 500 something? Yeah, I'm gonna throw this in the calculator real quick because I feel like it shouldn't be that much difference because the denominator didn't change. It's changing by a factor of 1.5 effectively.
It gave us the answer for the.
Yes. Four pi times 10 to the minus 9 times 8 times 15. Yes, I got what Patrick got, 16, so 1.641 times 10 to the 3 amps per Weber. Likely the reason why you're gonna get the same answer, even if you made a mistake there, is because the air gap reluctances are gonna be the thing that dominates this because they're gonna be so much larger. All right, so speaking of our air gap reluctances, those are the only two things we have left. So for our first gap, we have a length of 0.5 centimeter. Since we're not inside the core anymore, we only have the permeability of free space. 4 pi times 10 to the minus 9 henries per centimeter. For gap 1, our area is going to be our thickness, so that's 8 centimeters plus 0.5 centimeter times our width for that region, which is 10 centimeters plus 0.5 centimeter. For RG1, that's this guy right here. Yeah. Yep, not a problem. So 1/2 over 4 pi times 10 to the minus 9 times 8.5 times 10.5. 445.812. Actually, let's not do this like a jackass. 4.458 times 10 to the 5 amps per Weber. And then RG2 is going to be 0.3 centimeters over 4 pi times 10 to the minus 9 Henry per centimeters. So this is going to be 8 centimeters plus 0.3 centimeters. And this is going to be 15 centimeters plus 0.3 centimeters. And if you hadn't mentioned it a moment ago, I would have totally screwed that up. So thank you. I get 1.880. I'm rounding times 10 to the 5 amps per Weber. All right, so I'm going to call the left reluctance RTL plus RL plus RBL. So that's 3.108 times 10 to the 3 plus 2.487 times 10 to the 3 plus 3.108 times 10 to the 3, 8.703. Our mid is going to be RM plus RG2. So that's 1.641 times 10 to the 3 plus 1.880 times 10 to the 5. Looks like 1.896 times 10 to the 5 amps per Weber. And then our right is going to be R top right plus RG1 plus R right plus R bottom right. So let's see, RTR 3.067 times 10 to the 3. RG1 4.458 times 10 to the 5. RR 2.487 times 10 to the 3. R bottom right 3.108 times 10 to the 3. And I get 4.545 times 10 to the 5 amps per Weber. Doesn't, yeah, the other one's so small, it really doesn't do anything. Okay, so from here, I'm going to draw a little equivalent circuit thing. Here's our left. This is where my first coil is, so I'm just going to call this MMF1. Here's our mid. Here's our right. And here's MMF2. Now, as it's drawn, actually, it should have the opposite polarity. Let me just put something here that I'm immediately going to erase. As it's drawn, my second coil is down here. I'm just sliding it up to the side to make it look correct to my peon braid. Okay. So what's the equivalent reluctance seen by the first coil? So that would be with this thing turned off. So we would have, so let's call this REQ1 is going to be R left in series with R mid times R right over R mid plus R right, where that R mid times R right over R mid plus R right is just R mid in parallel with R right. So now I have to scroll up here and figure out what the hell those numbers are. So let's see. So that's going to be 8.703 times 10 to the 3 plus 1.896 times 10 to the 5 times 4.545 times 10 to the 5 over 1.896 times 10 to the 5 plus 4.545 times 10 to the 5. I got 1.425. If I type this into my calculator correctly, times 10 to the 5 amps per Weber. And if I'm trying to find REQ2, I turn this one off and look in where the terminals of MMF2 were. And so that's going to look like R right in series with R mid times R left over R mid plus R left. So throwing numbers into that, 1.896 times 10 to the 5, excuse me, plus hit the wrong button. Let's see, so R mid 1.896 times 10 to the 5 times 8.703 times 10 to the 3 over 1.896 times 10 to the 5 plus 8.703 times 10 to the 3. And I get 1.979 times 10 to the 5 amps per Weber. All right. So now finally, after finding all of those pesky equivalent reluctances, we can actually answer the questions that I gave you. What's the self-inductance of the coil? What's the mutual inductance? All that kind of good stuff, right? So the self-inductance of coil 1 is going to be the number of turns in coil 1 squared divided by the quantity REQ1, right? So since I believe there was 500 turns, this is going to look like 500 squared over 1.425 times 10 to the 5 amps per Weber, which is the inverse of a Henry. I get to be 1.754 Henrys. Is that what the problem says it's supposed to be? I'll be damned. L2 is just going to be N2 squared, excuse me, over REQ2. I believe our second coil had 300 turns, so it's going to be 300 squared divided by 1.979 times 10 to the 5 amps per Weber. Which I get to be 0.455 Henrys, just for the sake of argument. Let's check things. I got a very different number. So what mistake did I make?
I got a different total.
Okay, let's always a chance I just type stuff into my calculator too damn fast. So
I don't want to see.
no. All right, so let's check this again. So 4.545 times 10 to the 5 plus 1.896 times 10 to the 5 times 8.703 times 10 to the 3 over 1.896 times 10 to the 5 plus 8.703 times 10 to the 3. Yeah, I had a vastly different number as well.
Is it somewhere around?
4.628 times 10 to the 5. So if we plug that in, I should have caught that actually, because there's no way it could have been less than R right, which was 4.45 or 545. Yeah, so I should have noticed that looked wonky. So 4.628 0.194. Let me type this in just to be 4.628 10 to the 5. Yeah, 0.194. Okay, and then just to make sure, okay, seems legit there. All right. Yeah, now for the hard part, which I argue isn't really all that hard, but I'm a jerk. So
I just want to.
that's perfectly reasonable. Okay. So what we're going to do, we get to choose whether we want to find effectively the mutual inductance of coil 1 is seen by coil 2 or the other way around. Okay, so effectively what that means is, let me redraw my equivalent circuit here. We're going to leave coil 1 on. So this is our left. Here is MMF1, which is nothing more than N1 times I1. This is R mid. And then over here is R right. And I'm going to draw this coil in gray because it's not actually in the circuit at this point, okay? So this line that I'm drawing here in this blue greenish thing is the flux that's produced by our first coil. And this line that I'm drawing right here is the flux that's passing through our second coil due to coil 1. So I'm calling that flux 1, 2, okay? Now, as a separate thing here, because this is going to tell us the sign of our mutual inductance. This is the direction of the flux that would be produced by coil 2. Since flux 1, 2 and flux 2 are in the same direction, our mutual inductance is going to be positive. If they were in the opposite directions, our mutual inductance would be negative. Okay. All right. So what is that flux 1? So it's going to be the MMF divided by the reluctance seen by coil 1. Okay, so that's just going to be N1 I1 over REQ1. We already found. Okay, now I'm going to figure out what portion of that flux splits off and flows through that rightmost branch. And I'm going to do that using effectively current division. Okay, so I can say that phi 1, 2 is going to be phi 1, and now I'm going to apply the current division. So when we do current division, when we have two things in parallel, what's the rules? Anybody remember? Yeah, so current division is always when we have resistors in parallel. No, so current division tells me how much current splits off. So if I have some amount of current flowing into a parallel resistor network, I can figure out how much splits off and flows through each branch. So that's what I'm using here because I'm lazy and I don't want to do a bunch of math that I don't need to. So it's a proportionality constant, right? So for current division, when there are two branches, which is what we have here, it's going to be the resistance or reluctance in this case of the branch we don't want, R mid, divided by R mid plus R right. Is that okay, or do I need to derive current division for you guys and explain where this is coming from? You're all okay with this? Okay.
You did this, you like worked out in practice in the first house.
Mhm.
That was the 1/R.
Yeah, so you can do, 1 over, so this would be the same as 1 over R right divided by 1 over R mid plus 1 over R right, and then a little bit of algebra will get you to this. But I don't want to deal with a bunch of reciprocals because I'm lazy. Okay, so our flux linkage 1, 2 is just going to be N2 times phi 1, 2. And therefore our inductance L12 is just going to be our flux linkage 1, 2 divided by I1. So we're going to put all this crap together algebraically. So L12, don't know why I put a dot over the 1, is going to be N2 times phi 1, 2, where phi 1, 2 is just phi 1, so that is N1 I1 over REQ1. And then I have to multiply by R mid over R mid plus R right. And so I've done all of my substitutions. So all that I have written right here is effectively just that flux linkage 1, 2. And now I divide by I1. The I1s cancel each other out, which is why it's not important that I actually give you a number for the current there. And we have N1 times N2 times R mid over REQ1 times R mid plus R right. And we substitute in our numbers. So that is our mutual inductance. We could do it a different way. Yes, ma'am. No, they won't cancel out because, so the denominator of that fraction, like if we had R mid plus R right over R mid, then we could treat that as 1 plus R right over R mid, but we can't do it the other way around. And then we plug numbers in here, and I presume we're going to get whatever I say is on the answer sheet. The opposite, or the other way to do this would be to find the flux from coil 2, figure out how much of that flux passes through coil 1, and do effectively the same thing, and you'll get the exact same number. So it really doesn't matter which coil you leave on and which coil you turn off to do this. So the mutual inductance here is definitely the hardest part of this problem, and it comes from fundamentally understanding what mutual inductance means. Mutual inductance is the thing that couples the flux that's generated by coil 1 to what's passing through coil 2 and vice versa. Okay. So even if this part doesn't make a damn bit of sense on your exam, it's going to be 1/5 of that one problem. So worst case scenario, it's not going to bite you in the ass too hard by my design. All right, so there was a question about looking at problem number 5 as well. Are we okay to do that? Or you guys want to talk about this more, or what's up? This is the end of this problem, sure. Yeah. So if we look at the problem statement, just to be clear, I asked you to find L1, we found it. I asked you to find L2, we found it, and I gave you a symbolic representation of the quantity L12, and then I expect you to be able to plug that crap in your calculator, and you should get that 0.310 henries. So as far as I'm concerned, I'm done for that particular problem. All right. So problem 5 This is literally the exact same thing as we did in the example problem earlier today, like. Yeah, I'm kind of feeling lazy. I don't want to do it. I will if you guys, yeah. I mean, it is.
Calling you to actually plug in the numbers.
Sure.
The ending of that last.
Absolutely, yeah. So Jules wants me to throw the numbers in, so just for the sake of, nope,
Fine, I'm just wondering. if I'm putting-
not a problem. So N1 is 500, N2 is 300. Our mid is 1.896 times 10 to the 5. That whole thing is divided by REQ1, right? Yeah. 1.425 times 10 to the 5 times R mid plus R right. 1.896 times 10 to the 5 plus 4.545 times 10 to the 5. 0.3098 or 0.310. Yeah. Yeah, I'll try to get them up this afternoon. Mhm. All right, so is there any questions regarding your exam or anything like that? So I've told you effectively what you should expect to see on it. You are allowed to bring an equation sheet, 1 page, front and back, whatever the hell you want to put on there, as long as you wrote it, it's good by me. A standard 8.5 by 11 non-jackass sheet of paper. Absolutely, you can put whatever you want on there as long as you personally wrote it down.
It has to be handwritten.
It does have to be handwritten so that Jules or Catherine or somebody can't write an equation sheet and distribute it to the entire class. Yes.